All right. Thanks, Jeff, for the kind introduction. My name is Wenqi, and today I would like to introduce you performance optimization for an exciting new workload, namely retrieval-augmented generation. It is a new serving paradigm that addresses several fundamental limitations of LLM-only systems. And this is a work when I did internship at Google. So the key idea of retrieval-augmented generation, or RAG in short, is about pairing LLMs with this external knowledge database. So in this example, the user asks a question about Thomas Edison's invention. But now, instead of letting the model itself to answer the question directly, we'll now firstly use this question to retrieve from this external knowledge database. So conceptually, it's very similar to invoke a search engine call like Google or Bing. And more specifically, this retrieval procedure is done by a vector search on a vector database, where all these database documents are encoded to the vectors, and the query is also converted into vector format and compared against these database vectors. So in this example, in response to this query about Thomas Edison's invention, the retrieval procedure may found documents highlighting its contributions around phonographs, cameras, etc. And these documents will then be included to part of the prompt of the LLM, so the model can now generate a much more well-informed response. And by having this unique vector retrieval system in the pipeline, RAG achieves several unique advantages over conventional LLMs. First, the model is less likely to hallucinate because of the reference knowledge. And second, we can couple this model with more private data, so the model can actually provide more personalized answers to different users. And also, whenever there's no new data, instead of retraining the model over and over again, we can now simply update the database itself, which is both faster and also cheaper. And finally, there's also an argument that RAG can significantly reduce the cost of the LLMs because it can significantly reduce the model sizes, which is an argument I'm going to explain later on in this talk. And by having these many advantages, it's not surprising that RAG has gained popularity not only in academia, but also in industry, where all the major hyperscalers are racing to integrate RAG into their production systems. And as RAG is becoming the industry standard for reliable LLM serving, there's no doubt the efficiency for this new workload matters. So we wonder, what is the challenging point about RAG serving? Because shouldn't it be straightforward to just combine these LLMs with the retrieval systems? Well, it turns out RAG serving can be far more complex than it appears. Since the invention of RAG, there have been numerous RAG algorithm variants, some proposing adding new model components to the pipeline, while others propose fancy retrieval patterns. And these models are evolving so rapidly, so not a single RAG algorithm configuration can outperform all the other ones across all dimensions. And also, these different components are running on heterogeneous hardware. For example, we can use different types of ML accelerators for these various models, and also CPUs or even accelerators for this retrieval as well. So because of this very different algorithm configuration, it turns out the workload characteristic of different RAG algorithms also differ a lot. And they look like completely different performance optimization problems. So the first part of this talk is about studying the workload characteristics of different representative RAG workloads. And specifically, we study 4 very representative RAG serving paradigms. The first one is RAG with internet scale retrieval. In the second case, instead of having very large database, we study RAG for personal documents or enterprise data. And in the third case, instead of initiating just one retrieval at the beginning, we also study RAG with iterative retrieval, where the model itself can initiate this iterative retrievals during the generation process. And in the fourth case study, we also study RAG pipelines with additional models, including query render and result re-ranker models. And today, for the sake of time, let's take a closer look at the first 2 cases. So the first case is RAG with internet scale retrieval, or connecting the model to Google or Bing. And there's an argument that RAG can actually save the model parameter by 10 times, but still achieve the same generation quality. And the reason behind this is that the LLM basically is a knowledge compressor, so it tries to remember everything it has seen in the training corpus. But now if we can inject all this knowledge from this external knowledge database, then we don't need that large model at all. And the workload here is pretty simple. It's a 3-stage pipeline. We have this retrieval phase at the beginning, And here we take this configuration from a DeepMind paper that contains trillions of tokens, and that translates to 100 terabytes of raw database vector. And after that, we will have these two phases of LM inference. The first phase is known as the prefix or the prefill phase, which basically computes the prompt. And the second phase is the decoding phase, where the output tokens are generated one at a time. So now let's take a look at the workload characteristic of this example. So in this plot, the x-axis shows the different number of queries at the beginning of the generation process. There can be multiple queries at the beginning because the user question can be complex or vague, so we may need to break it down into multiple queries at the beginning. And then the y-axis shows the time breakdown between retrieval and this inference components. And as you can see here, for this small model, even with only one query vector at the beginning, it already becomes the main performance bottleneck. And if we adopt this multi-query retrieval technique, the bottleneck is only going to be more dominant. So the takeaway message here is that after years of efforts in optimizing model inference performance, now the next bottleneck is fast retrieval, especially at very large scale, which presents further research opportunities for the architecture community. And the good news is that I already found very interesting papers in ISCA this year about addressing this retrieval performance. So feel free to also check this works out. Now let's switch to a very different use case of using RAG. Now instead of connecting this model to the internet, now we want to apply RAG to more personal documents. So you can imagine a workload where users just upload their documents to a cloud service and start asking questions about these documents right away. Another way to do this is that we can just put the entire documents into the prompt of the LM, but still it turns out this is a very expensive approach just because of the number of tokens we have to process by a very large model. So a more efficient alternative here is to use RAG, where we construct this database at the runtime and then only retrieve some relevant passages into the prompt of the larger LM. And by reducing this prompt size, we can actually save the performance cost by hundreds to even thousands of times and still achieve similar generation quality. So how does this database construction work? Well, it's pretty simple. So we have some documents and we first chunk them into shorter passages. And for each passage, we'll use a small bird-style encoder model to turn this into a vector representation. And here, because we're using a small encoder model, even we want to construct this database at the runtime, it's still much cheaper compared to the naive long context language model approach. And here, because we're talking about small documents, the size of the retrieval here is actually millions of times smaller compared to the hyperscale just seen in the first case study. So what's the performance characteristic of this case study? So in this plot, the x-axis shows the different document lengths ranging from 100K tokens all the way to 10 million tokens. And the y-axis breaks down the time consumption. And here we use a pretty small encoder model that is 500 times smaller than the main generative LM. And still, you can see that as the document length increases, the encoding time still increases and eventually dominates the time consumption. So it means even a very small model in the RAG pipeline that is hundreds of times smaller than the main LM can still become the main performance bottleneck here. And the second interesting observation here is that if you try to look at where is the retrieval time in the bar, you can find it's almost invisible. And this is even given the assumption that we're using a brute force search here without an index at all. So in contrast to the first case study where retrieval performance is absolutely crucial, here retrieval performance is not important at all. For the sake of time, I cannot go deep into the rest case studies, but in short, for the third case study where we have iterative retrievals during the generation process, we found that the ML accelerators will remain idle when waiting for this retrieval result. So there's a delicate trade-off when tuning the batching policy of retrieval, which will have a trade-off between the retrieval efficiency and generation efficiency. And for the final case study where we have additional models in the pipeline, we find that even if we have only a very small query writer model in the pipeline, can still significantly increase the time to first token latency. So across all these examples, we can see that the workload across different RAG algorithms really differ a lot and look like completely different sub-problems. So a natural research question here is that how can we design a RAG system to accommodate all these very different RAG workloads? Well, before solving the problem, we first need to have a good problem formulation. Essentially, we need a workload abstraction that can capture all these different RAG algorithm variants. And to this end, we proposed RAG schema, which is a unified workload abstraction that mainly describes two things. The first thing is that what are the models in the pipeline, because there can be more models than the main generative LLM. One example is the database encoder model we just seen. And before retrieval, we may have this query writer model to rephrase users' question. And after retrieval, we may have this re-ranker model to further rescore the relevance between the retrieved documents and the user's question. And in terms of retrieval itself, there are several interesting attributes. First is the size of the databases, can really vary by 1 million times depending on your use cases. And also, we may have more complex techniques of retrieval, including multi-query retrieval and iterative retrievals. So now with a good problem formulation, we're ready to solve the performance optimization problem. And to this end, we propose SRAGO, which stands for Retrieval-Augmented Generation Optimizer. So given arbitrary RAG algorithm described by RAG schema, and also your hardware resource budget, RAGO can navigate the system design space in order to search for the performance Pareto, and also return the optimal system configuration. Now let me introduce you the system design decisions in RAGO with an example. So the first design decision here is how do we do the task placement? Essentially, do we want to co-locate different models in the same set of accelerators, or do we want to disaggregate them on different accelerators? Well, the answer is that it depends. For example, the prefix phase of the LLM and the re-ranker model may be co-located on the same set of accelerators because first, they share the same performance metric of time to first token latency, and second, they're both computational intensive. On the other hand, the decode phase and the prefix phase of the LLM may be disaggregated over different accelerators because the decoding phase optimizes a different metric of time per output token latency, and also it's much more memory bound instead of being more compute bound. Now, once we settle the task placement, the second decision is resource allocation. Essentially, how much amount of accelerators do we want to allocate to these different models, and also the CPU resources for retrievals. And finally, given a burst of user requests, we need to settle the batching policy. Given a burst of requests, we can either use the same batch size across all the stages of RAG serving, or we can break it down to micro batches. And both are valid options depending on whether the performance goal is more about latency or more about throughput. So how does RAGO find optimal schedules? Well, in short, RAGO is a cost model-based optimizer, so it's conceptually similar to a database query optimizer. It has an inference performance model currently supporting TPUs and GPUs, and also a retrieval performance model currently based on CPUs. So these are very well-tuned refined models, so given some input workloads like model sizes, database sizes, sequence lengths, etc., we can estimate the system performance on a given hardware backend very precisely. And after that, we can assemble the component level performance to form the entire RAG serving performance. Essentially combine different strategies of each RAG component, and then given users' performance requirement, we will then return which are the best system design decisions for the specific RAG workloads. Now let me just show you some performance results on the second RAG case study where we have this user-uploaded long documents. And here, the x-axis shows the time to first token latency, and the y-axis shows the throughput. And here, each of this curve basically represents a single resource allocation strategy, and the different points on a single curve basically represent different batching policy that controls the trade-off between latency and throughput. And as you can see here, for different resource allocation plan, the throughput can vary by up to 64 times. For example, the naive plan on the bottom basically only allocate little resources to this small database encoder model, just because this model is hundreds of times smaller than the main generative LLM. However, as we have seen before, this small model can actually become the main performance bottleneck in the pipeline. So instead, RAGO will navigate the system design space to do proper resource allocation, and that will lead to 64 times of improvement in throughput and also 9 times of improvement in terms of latency. For the sake of time, I cannot cover all the evaluation, but the key takeaway message is the same. we need appropriate task placement, resource allocation, and batching policy that is tuned for the specific RAG algorithm and hardware backend. So to summarize, RAGO bridges the gap between the fast-evolving RAG algorithms and the underlying system support. We first showed how different is the workload characteristic between different RAG algorithm configurations. And then we proposed RAG schema, which is a unified workload abstraction that can describe all this RAG algorithm in a unified pipeline. And finally, we proposed SRAGO, which is a cost model-based optimizer that can systematically address inference performance for arbitrary RAG workloads. You can check out our project artifact in this URL. And with this, I would like to conclude this talk and also happy to take your questions.